Hello everyone, thanks for joining my listening. Today I'm Zhao from Violating. Today I'm going to present our work detecting third-party component usage violations in IoT firmware. And it's a joint work by Georgia Tech, Zhejiang University, and UC Los Angeles. So first, as we all know, third-party components are widely used in IoT firmware to shorten the development cycle. And for example, the BC box and OpenSSL are two most popular third-party components used in IoT devices. But I want to say third-party components usually have very strict usage specifications. For example, it requires you to check the return value, and sometimes it requires you to check the arguments that are used in the function. And violating the usage specifications of third-party components can bring serious problems. For example, the null pointer dereference. And here are two real-world vulnerabilities caused by misusing the third-party components. So given the serious problems of usage violations, it's really important to find them in IoT firmware. Okay, so first I want to introduce 4 kinds of usage violations. We classify them based on previous works and our observations. So first one is the deprecated API violation, and also return value violation, argument violation, and the causality violation. Okay, so if we want to build a practical system, we still have 2 major challenges. The first challenge is how we can extract API specifications from documents, because as we all know, documents are written in natural language, so which cannot be easily understood by computers. And we find previous works have already proposed many methods to solve this problem. But we find some methods already perform well on some well-formatted documents, and they are really hard to handle some unusual API specifications. Okay, so the second challenge is how to perform the analysis on closed source binaries. As we all know, binaries will lose much information when comparing from the source code. And we find previous work only focus on source-level API misuse detection, which means we cannot directly use their works to apply to our task, and which brings more challenges to our task. Okay, so to solve this problem, we propose UVScan. UVScan is the first automated and practical system to find usage violations in IoT firmware. And as you can see from this figure, it has 2 pipelines. So first pipeline will first get the API specifications from documents, and then will transfer into programming expressions. So programming expressions will be easily understood by our analysis engine. And for the second pipeline, we will first encode the firmware to get the internal logical information, and then we can easily perform the check on the encoded firmware based on the API specifications. Okay, so I first want to introduce the first component, API specification extraction. For this component, we want to get the API specifications from the TPC document. And it mainly has 2 steps. The first step is to get relevant API descriptions and filter out irrelevant API descriptions. Because based on our experiment, we find the irrelevant API descriptions will heavily impact the final performance of UVScan. And we find the previous research indicates that relevant API descriptions usually have a very strong sentiment. We find these findings work in many cases, but there are some exceptions. For example, this sentence has a very strong sentiment word, should, so you can regard it as a relevant API description. But if you know the context, you will know actually the entity referred by the pronoun is not related to the API. So actually, it's not a relevant API description. And to solve this problem, we introduce the co-reference resolution model. Co-reference resolution model means to find the real entity referred by each pronoun. We here introduce the WL co-ref. WL co-ref performs really well on resolving the co-reference in the TPC document. And after resolving the co-references, we design a sentiment-based model. We mainly use the bidirectional long short-term memory model with the multi-head self-attention mechanism. And with our design, we can get the sentiment of the target sentence more accurate. Okay, so we have already get the API descriptions, but we still need to get the precise API specifications. Here is a real-world example. if you want to understand the second half of the sentence, you need to first understand the first half of the sentence, which cannot be easily achieved by just using the pattern match. So in this task, to solve this problem, we introduced the machine reading comprehension system, which is a really hard topic in natural language processing. And a machine reading comprehension system is designed to enable computers to understand the context, understand the text, and also can respond to some questions raised by the people. So the key design for a machine reading comprehension system is to provide a set of questions you want to ask. So we designed 10 kinds of questions based on the features of different usage violations. And here is a real-world example of the labeled third-party component document. And as you can see from this table, it has two kinds of answers. The first kind of answer is directly extracted from the document. And the second kind of answer is no answer, which means we cannot find the answer from the document. And our machine reading comprehension system is developed from the Roberta model, which is a very famous model. And we fine-tune the model with many labeled third-party component documents. Okay, so we have already get the API specifications, but the problem is that they are still written in natural language, so which cannot be understood by our machines. So we decided to transfer them into the machine-readable representations, which we actually call them programming expressions. And the format of these programming expressions are defined by ourselves. Our method is we first use the part of speech tagging to annotate each word in an API specifications. And we then create a dependency tree by combining words with a close relationship. As you can see from the tables, must be free, there are verbs, and we then combine them together and put them into the root node of our dependency tree. And we then will transfer the dependency tree into the programming expression. We mainly collect many common phrases, and then we will map the root node into the operation field. For example, the must be free, we will map it into the call operation. And the leaf node, the content in the leaf node will be slightly changed and put into the argument field. Okay, so we have already get the programming expression. So our next step is to perform the analysis on this programming expression, based on these programming expressions. And as I mentioned before, the binary loses much information when comparing from source code. So our idea is to retrieve the internal logical information. So we here introduce the data log. Data log is a query language. You can regard it like, it's very similar to the SQL language. And for the data log facts, you can regard it like the data that's stored in the database. And for the process of encoding the binary into data log facts, you can regard it like that we first get the data in binaries, and then we store the data into a specific database, and then we can easily perform the check on these generated facts. Our first step is to encode the binary. We here introduce the DDSM. DDSM is a very nice job, and it provides a set of standards to encode the binary into initial data log facts. But we find it's not enough because we want to know the operation of some specific registers. So we customize some rules, and as shown in the right figure, here is an example of a rule that checks if the return value less equal than 0. And it mainly has 3 conditions. So we will get the corresponding results once these 3 conditions are met. Okay, so next we design 4 trackers based on the features of different usage violations. For example, for the return value violation tracker and the argument violation tracker, we mainly focus on the operations of some specific registers. And for the causality violation tracker, we mainly focus on the functions that are called before or after the API, and also the operations under certain return values. Okay, next we evaluate the performance of key components in UVScan and also the overall performance of UVScan. First, we evaluate the API extraction accuracy. We mainly compare UVScan with 3 systems: Advanced, region-based neural network, and Alex. Advanced is the first work that uses the sentiment to classify the API descriptions. And as you can see from this table, UVScan has better performance, it has another 3 systems. Okay, next we evaluate the overall performance of UVScan. We mainly use 2 datasets. The first one includes 77 real-world usage violations. And the second one, we want to enlarge the first one, so we created the second one. It includes 69 manually created usage violations. And we also compare UVScan with 3 systems, the Advanced, API-SCEN, and Apex. And these 3 systems are performed on the source level, while UVScan performs on the binary level. And also, UVScan performs on the binary level. Its performance is very close to Advanced, and it's much better than another 2 systems. It's reasonable because another 2 systems, they get the API specifications by analyzing a large amount of code, which means sometimes the API specifications are not accurate. Okay, so next we perform a large-scale analysis on more than 4,000 firmware images we collected from a private company. We have 2 research questions for the usage violation problem on IoT firmware. So the first question is, which are the most prevalent usage violations in IoT firmware? And to answer these questions, we first identify more than 27,000 potential usage violations. And we find the deprecated API violation takes the majority of the overall usage violations, accounting for 41%. And also the causality violation and the return value violation are also widespread in IoT firmware. Okay, so our second question is, what are the practical impacts of usage violations on IoT firmware? We classify them into 3 categories. The first one is a security vulnerability. Because we find some usage violations can be used to perform attacks, and we do some case studies in our paper to prove it. And we find also nearly 15% usage violations are just bugs, which means they cannot be used by us to perform attacks. Maybe it can be used by you to perform attacks. And we also find nearly 80% usage violation actually have no impact on the devices. Okay, so in conclusion, we propose UVScan is the first automated and practical system to find usage violations in IoT firmware. And we also performed the first large-scale analysis on this problem, and we find 7 CVEs. Thank you for listening. Any questions?